Now we are. Okay, so let's start. So today is going to be, so last time we sort of developed the linear algebra necessary to sort of justify why we are referring to this as sort of spectral expansion or spectral analysis of these random walks, etc. Because these matrices had some nice eigendecomposition, and these eigenvectors and eigenvalues are quite useful when you want to study how this matrix behaves on things. So I'll do a brief recap, and today the main objective of today is going to be to finally understand when you want to say a random walk mixes well, what do we mean by that, and how are we going to analyze that, and hopefully we'll then be able to give at least analyze the randomized algorithm for ST connectivity that I mentioned the last time. Anyway, we'll do a brief recap and just go over all the things that we do. So, like we mentioned last time, if you have an undirected graph G, need not be regular. There is an associated random walk matrix, which refers to this what is called the standard random walk matrix, in the sense that you're doing a standard random walk in the sense every vertex is going to choose a uniformly random neighbor and move there. There's no associated weights, blah, blah, blah. If there are weights, then you'll have to modify your degree matrix appropriately. It should be the weighted degree is what should show up there and so on. Okay, but let's ignore that. We're going to be dealing only with standard random walks. Okay. And once you have an operator, you have like two notions that you can, or rather three notions actually, but this operator sort of acts on rows and it also acts on columns. And these two have slightly different meanings. And the first thing is, in some sense, if you have a function f, which is like a function on vertices, it's like assigning some values to every vertex, then in some sense mf looks like a diffusion. It sort of replaces every vertex value by some sort of averaging of what happens nearby. So if you're dealing with things that sort of have the diffusion-like flavor, then you're thinking of column vectors and M acting on column vectors. Okay. Whereas on the other hand, if you think of it as rows, then it's like the evolution of the probability distribution after you take one step of the random. So these two are not quite the same, but they have very similar flavors.
So when are they the same?
So for instance, if M was actually the symmetric matrix, okay, then M, so basically you can think of P transpose M as just the transpose of MP, or rather M transpose times P's whole transpose. So if M transpose and M are the same, then it's sort of the diffusion behavior and the random walk behavior are basically the same. So in fact, this is the reason why when you're dealing with regular undirected graphs, things are like super nice because you can just completely freely move between the row perspective and the column perspective.
So the adjacency matrix is anyway symmetric for undirected graphs.
Yeah.
If the degrees are all the same, every entry scales.
That's right. So the row normalized adjacency matrix also turns out to be symmetric in that case. And that's the advantage. So if you're dealing with a deregular undirected graph, the matrix M itself is symmetric. So its behavior on rows and behavior on columns is identical. So you can just ignore that part. But there are situations where you might purposefully make a graph like irregular to make certain analysis go through, but you somehow want to say that morally things happen the way you expect it to happen. And that's the reason why it's sometimes convenient to work with this more general notion. Okay. And in fact, as I had briefly mentioned last time, is that whatever I'm saying is just a subclass of what is usually said in a Markov chains course, where you often in a Markov chains course, you will assume that the Markov chain is reversible and then make a whole bunch of claims. And the reversibility will become some statement of the form pi m equals m transpose pi. But we had a particular setup in mind, which was the undirected graphs, and somehow eventually told ourselves that, oh, we are in the reversible situation.
So this case when the left action, right action are turn out to be the same for symmetric matrices. I mean, okay, it's just linear algebra that when it's symmetric, it turns out the same. But is there like an English interpretation to say like what does it mean that this averaging behavior, diffusion, and this evolution thing turn out to be the same? Is there anything more to it? Or is
So
it-
hopefully once we do an analysis today, let me come back to this question after that. So it's a good question in the sense that in terms of algebra, yes, I mean like M transpose and M are the same, but in some sense, why is it as probability distribution? So long story short, it's the following. It's always like throughout spectral analysis, what people often do is they think of the spectrum from the perspective of the action on columns. Okay, so it's always the norm of mx as in comparison to the norm of x, etc. But if something is an eigenvalue, it's an eigenvalue whether it's the left action or the right action. So in principle, we could have turned the whole thing around and just focused on, suppose I want to use the spectral theorem on the row vectors as opposed to the column vectors. Then hopefully there is some related inner product under which M transpose happens to be self-adjoint. You will have your set of eigenvectors. One of your eigenvectors happens to be your stationary distribution, etc. You would like the rest of the analysis to sort of happen, and it does. Now, if you take that perspective, the two inner products with respect to which M is self-adjoint turn out to be identical in the case when M is symmetric. Okay. Anyway, after we do the analysis that we're going to see today, hopefully this will make things a bit clearer.
Also, a similar question about this name reversible. Does it mean that like we can go by half?
Yeah, so reversible in a Markov chain literally means the following, in the sense that you sort of want to say, if you construct the new Markov chain where all arrows are just turned around, you want the stationary distribution to be the same.
Okay.
Basically, yeah. So that's why it's called reversible. Yeah. Okay. Good. So we notice that from the perspective of column vectors, the trivial eigenvector was the all ones vector, because if you average a constant vector, it's going to stay constant. But whereas from the perspective of row vectors, which are probability distributions, the trivial in quotes probability distribution such that pi transpose M equals pi transpose is this particular stationary distribution. This is like the canonical stationary distribution. And it's often convenient to think of this as a process where you're just picking an edge at random and choosing an endpoint. If you think about what is the induced distribution that you have on vertices, that is what this pi is. Okay. And pi is at the moment a stationary distribution. What we are going to try and do is come up with some necessary conditions to somehow say that pi is the stationary distribution. At the moment, it feels like maybe there are other distributions such that, that will also satisfy this particular relation.
The sum over degree there in the denominators for all vertices.
Sorry, the denominator is like summing over vertices B, and this is just some, yeah. So think of the denominator as basically twice the number of edges. Yeah. Okay, good. And then we define this inner product, which we sort of told ourselves that no, this is the right inner product to work with, which is just defined as the standard inner product, but scaled with this pi x. Okay. Though I didn't formally do it, I mean, like you can check that this satisfies all the properties you want an inner product to satisfy. That is, it is linear in the first part, it is linear in the second part, and the inner product of f with itself will always be non-negative. So these are three properties you want inner products to satisfy, and all of this is true for this as well. And this also has a very nice interpretation, which is you're looking at the correlation of the functions f and g across edges. That is, you pick an edge at random and you're asking what is the expected value of f of x times g of x, f of x times g of y, where xy is the edge. Okay, and as like sort of just a matrix or a vector matrix equation, this is basically just saying that you're writing it as the inner product. Oh, sorry, I was talking. I mean, here, I mean, we're not introduced M yet. I mean, if you're just looking at the inner product of f and g, you're really looking at, you choose an x at random, and then according to the stationary distribution pi, and you're looking for f of x g of x. Okay.
Ramprasad.
Yeah.
A little late, but yeah. So f and g are now here being looked at as functions from the set of vertices to the right.
Yeah. So I'm thinking of f and g as something from
Right.
V to R, and I might interpret this as a column vector, where the Vth coordinate is the function value at V.
Right.
Yeah. Okay. So that's what the inner product just refers to. You sample X according to the stationary distribution. That is the distribution above, this canonical stationary distribution, and look at f of x times the expected value of f of x g of x under this distribution. And we'll be dealing with norms, and whenever you, I might sort of end up forgetting to write this pi all the time, but it will always be the norm with respect to this inner product. Okay, and now comes the bilinear form.
The inner product only makes sense for pi being the stationary distribution.
The inner product would have still made sense for any probability distribution pi, but it's going to be convenient to work with this because under this distribution, the vectors you care about will be orthogonal and stuff like that. Yeah. Okay. And now finally, I want to talk about the bilinear form defined by the matrix M. And this has a nice interpretation that, if you pick an edge xy at random and look at the correlation of f and g on the two endpoints, that's exactly what this bilinear form captures. Okay. And we saw how, when we were looking at the expander mixing lemma or something, the left-hand side turned out to be exactly this, where f and g were instantiated to be the indicator functions of s and t respectively. Okay. And then the consequence of the spectral theorem was that, by the way, this, whatever, it's easy to note from this that this also looks like MF and G. Normally, if you think about, if you think about an arbitrary matrix and with respect to some arbitrary inner product, usually you will replace this M with M transpose. That is what will make this equation true. Okay, but it somehow suggests saying that under this inner product, M sort of behaves like a symmetric, like M transpose equals M in some sense. Okay, so this property is said to be self-adjoint with respect to a certain inner product if this holds. And the general spectral theorem works for self-adjoint operators with respect to some inner product, and it tells you that under this inner product, you actually have a basis of eigenvectors. You have a bunch of eigenvalues and the corresponding eigenvectors. All of them turn out to be real. They're all real valued. And furthermore, these eigenvectors are actually orthogonal to each other. And you can also normalize it by just scaling each eigenvector appropriately. Okay. And
you don't care about eigenvalues being distinct, except for the first one.
In fact, I'm not going to care about them being distinct at all.
So all you care about that they form, like the eigenvectors form an eigenbasis.
That's it. Yeah, the eigenvectors form an eigenbasis, and it will allow me to take any vector, decompose it in this eigenbasis, and then its action is very clear. Like each component gets scaled by the corresponding lambda. Okay, and as a matrix definition, this is what the self-adjointness means. It's just pi m equals m transpose pi. This is something that I always keep forgetting. So usually the way I remember is I try to look at, if I were to write f times mg with respect to pi, what do I write? So this is going to be f transpose times, I stick a pi in the middle and then I put the second vector. And so the other direction would be like, I want to write this as maybe mf and g. In that case, I would be writing f transpose, m transpose, stick a pi in the middle and then I put a g. And this should be true for all choices of f and g. And that will basically tell you that pi m should be equal to m transpose pi. Okay, good. All right. So, and finally, we can define what the spectral gap is. This is the somehow this. I realize that every time I have written this particular definition, I've always written it in a slightly different way because I'm trying to figure out, I'm trying to take my mental picture and make it into some equation. What it really means is the following. All your eigenvalues are between -1 and +1. Okay, there is one stupid eigenvalue at +1. I want to remove that and I want to know how much can I shrink this so that I'm guaranteed that all eigenvalues the rest of the eigenvalues are all in that range. Okay. Basically, this is completely determined by the two extremes. It really cares about what is the rightmost eigenvalue you have. I mean, the greatest eigenvalue you have and the smallest eigenvalue you have. Okay. So the game is really between just these two values, lambda 2 and lambda n. Okay. And you want to know amongst lambda 2 and lambda n, what's the largest absolute value you could have.
So lambda n can be minus. Is minus 1 and
yeah, towards the end of the lecture, we're going to look at when will lambda 2 be equal to 1, or when will lambda minus 1, lambda minus n be equal to minus 1. These are things that we will see. And hopefully in the problem set, you will also see, can it be the case that lambda 2 itself starts becoming negative? Or not negative, maybe it's like 0 onwards and stuff. So we'll try to get a sense of, what these lambdas mean.
So some of like when lambda n is minus 1, it means that it's very bad exponent. So from this result, we will get that.
Okay, hold that thought. So at the end, we are going to look at when lambda n will be minus 1. So, okay. But basically, this is what this lambda refers to. You basically want to say, what is the guaranteed shrinkage you have for a vector that is orthogonal to the all ones vector? That is, I apply M and I want to say that any vector, as long as you promise to me that it's orthogonal to the all ones vector, the length shrinks by this much. And the worst case shrinkage is what lambda g refers to. And if you think about what is the vector x that maximizes this, it will basically, you'll basically choose either v2 or vn, depending on which one had larger absolute value. Okay. And we stated the EML theorem for expanded mixing lemma for these undirected, possibly irregular graphs, where we said that if you take alpha to be the density, so sometimes this pi of s is used to refer to the mass that s takes under the distribution pi. By that, what I just mean is you pick an x according to pi and ask what is the chance that you actually fall inside your set s. Okay, and if alpha is pi of s and beta is pi of t, then if you pick a random edge and ask what is the chance that your two endpoints lie in s and t respectively, versus you just pick two independent x and y and ask what is the chance that x is in s and y is in t, these two values don't differ by much. Okay, there is some sort of error term, and depending on the context, this error term might be small. So, okay, and one thing is clear that if lambda is small, then the error term is also small. Okay, so now what we are going to do is we are going to start talking about random walks on these graphs. And what we want to ask is just the following. I start with some probability distribution P0 of your choice. Maybe your P0 is basically, you started from a certain vertex, in which case P0 is just like it's zeros everywhere except that one vertex, and that one vertex you have one. Okay, but you could choose P0 to be any distribution that you care about. Okay, and then you keep taking one step. So after you take one random step, the current vertex is distributed according to some distribution. I'm going to call that P1. And then you take one more step, it's going to get distributed according to P2 and so on.
So this is all left. But,
yeah, so every yes. So I should really be thinking of them as row vectors, and P1 transpose is like P0 transpose times M, and so on. Okay, and I want to know what is the if I keep repeating this, does it sort of converge to yeah?
So are you going to look at this as M times, I mean, again, this action?
So in general, Pi plus 1 transpose is equal to Pi transpose times M. This is the evolution of probability distributions according to the underlying random walk.
No,
so if you want to think of it this way, this is the same thing as saying Pi plus 1 equals M transpose times Pi. They're both the same.
Right.
Yeah. Okay.
Yeah.
And what we want to understand is, I mean, like one way to somehow convince ourselves that there is a unique stationary distribution is that you basically somehow, if you are able to show that you start off with whatever distribution you want, and just keep repeating this process, you will actually start converging to this one distribution. So that might be another way in which I feel like some water is dripping. Okay, whatever. Okay, so this is what we'll have. So this is the question we would like to answer, and it will turn out that this is actually true as long as there is some spectral gap. By that, what I mean is I just want the spectral gap gamma, which was 1 minus lambda, to just be positive. Like as long as it is strictly greater than 0, this convergence will happen. But I also need to specify when I say convergence, like I need to have a notion of distance. I mean, like in the sense that I want to somehow say that these probability distributions get closer and closer and closer. But what do I mean by closer? You know, and of course, you can always come up with your own definition. But sometimes, depending on what you intend to use this for, there are certain standard definitions you may want to work with. Okay. And one definition that just works all the time. I mean, like this is a very important definition of distance between two probability distributions is this notion of what is called total variation distance. Okay. Formally, this is what total variation distance is defined as. Okay. You run over all points in your sample space, okay, which is the V, and you just look at the difference between the two probability distributions, but take their absolute value. Okay. Now, obviously, if I didn't take the absolute value, this will be 0. Because the P sum up to 1 and Q sum up to 1, but you're always taking the right sign in some sense. And there is a half for some technical reason, but you can ignore the half, and it's like a decent definition anyway. So what is the sort of intuitive, maybe a pictorial way of representing this is like if I think of this as a graph where this is the y-axis involves the probability mass and x-axis in some sense is the cartoon for the various sample points or other points in your sample space, then maybe your distribution P sort of looks like this. Okay, and maybe your distribution Q sort of looks like this. Okay, and so what sort of this total variation distance refers to is the area of this sort of shaded region, like the gap between P and Q that you have through. Okay, so as you can imagine, if P and Q are the same, obviously it's going to be 0. But the more different P and Q are, it's going to be something non-zero, and you get some.
Why the half?
Why is the half? The half is because this also has a dual representation, which is actually very useful when it comes to where you might want to apply this. Okay, and the dual representation is the following. It's sort of this total variation distance captures the following. You want to suppose distinguish between the two distributions P and Q. Okay, what does distinguishing two distributions mean in certain applications you care about? So one way to say that is like you are free to choose an event of your choice. You want to say this event is satisfied by these vertices, it's not satisfied by these vertices. That's something completely up to you. Like amongst all possible events, how different is the probability of this event being satisfied when you take these two distributions? That is, if you sample X according to P, you can ask the probability of the event being true is something. But if you sample X according to Q, maybe the probability of the event being true is something. The worst gap you can create here is actually this total variation distance between P. In fact, the event is just going to be on points where P is bigger than Q, the event is true. Otherwise, the event is false. Or some such thing. I think once you write it this way, the half sort of shows up or something like that. Or maybe the half shows up when you replace this event with some function between -1 and 1, and you replace the probability by an expectation. I mean, there's some reason why the half is there, but we are not going to really fret too much about it. All right. So let's ask the following. We really are going to ask, as the probability, so recall that P0, P1, P2, etc. is the evolution of the probability distribution as you take many steps of the Markov chain of this random walk. And what we are going to try and capture is what happens to this total variation distance between the distribution I'm currently at and the stationary distribution? I first want to get an expression of this, and then ask what happens if I make t larger and larger and larger. Is this total variation distance becoming smaller and smaller? That's what I would like to do. Okay, so is it clear so far? Okay, so there is some jugglery that we are going to end up doing, and hopefully in your problem set, I will try and give a slicker way of doing the whole thing. But I think this is instructive. Okay, so the thing is, when we are dealing with the random walk matrix, etc., it was always convenient to work with the distribution like given by pi. Always deal with expectation whenever possible under this distribution pi, etc. Whereas the stupid total variation distance looks like a uniform thing. So the first thing I'm going to do is I'm going to somehow massage this so that I can write the same value as some expectation over the distribution pi. Okay. So what I'm going to do is I'm going to write this as half times x. I mean, I want to put a pi x here, because expectations according to pi looks like pi x times something. Okay. And so what I do is I just divide what I have here by pi x. So I'm going to write this as pt of x by pi of x minus 1. Okay. And this is half times, for now I can write this as the expected value of x according to pi of the absolute value of pt of x by pi of x minus 1. Okay, just to rewrite what we want in terms of something that we can control. Okay, and I want to write this as a so I'm okay. So let's do a brief detour. So when we were talking about something like f2, or what were we doing? This we were writing is that the expected value of x drawn according to this pi of f of x the whole squared, the whole power half or something. That's eventually what it turned out to be. In general, this could be your notion of a kth norm. When you care about the kth norm, what you do is you again draw x according to the distribution you care about. Okay, and then look at that power k and take the final expectation power 1 over k. So the reason I'm doing all this is like I want to write this as pi inverse times pt minus the all ones vector, but the one norm, again, everything according to the distribution pi. Because pi inverse times pt is the same thing as you take your column vector pt, but then scale every entry by pi. Again, pi just refers to the matrix of this thing. Someone might be fair to ask me, what do I mean by pi inverse? What if one of the entries of pi is actually 0? That maybe the graph is like those vertices are not even connected to anything. So there are ways to fix it, but for the moment, let's assume that if the vertices aren't connected to anything, they have no business being in the graph. Okay, I'm just going to ignore those things. The right way to do this is you think of pi inverse as the pseudo inverse. The sense that wherever you can invert, you invert. Things that are 0, keep it as 0, and you basically have to notice that whatever I'm saying today, nothing changes. Okay, but this is what is going to happen. And the nice thing about norms is always that this is at most half times the 2 norm of pi inverse times pt minus 1. Okay. So once you have norms as expectations, as you increase your k, your norm only increases. That's one way to tell yourself. The more basic way to tell yourself is basically, this is just Jensen. Okay, this is what the function x squared sort of looks like. So you notice that the chord is always above the graph. So this tells you that the expected value of f squared is bigger than the square of the expectation. Okay. So if you just work out that or something, that's another way of just getting something like this. Okay, and good. So therefore, what we have somehow managed to do right now is replace the total variation distance that we wanted to care about This is what we want to get a sense of as t keeps increasing. We've somehow managed to write this as the 2 norm of some vector. Ignore this half that is showing up. Okay, and it's just that with respect to linear algebra, 2 norms work nicely. It's easy to get a handle on what this 2 norm looks like. Okay, and now what I would like to know is that I want to somehow show that as t goes to infinity, as t becomes larger and larger and larger, I want to say this keeps shrinking and shrinking and shrinking. Okay, now I want to give a sense of what is the dream situation. The dream situation could be like whatever this vector is. Okay, it happens to be a vector orthogonal to the all ones vector. And somehow as I keep increasing t, it's like as if I am applying the matrix M to this. Then the whole notion of spectral gap will tell you that every time I do this, it shrinks by a factor of lambda. That would be the dream situation. And we'll basically show that the dream situation just works. Okay, so let's get a sense of what do we know about things. So the first thing is that the evolution of P goes like this, like PT transpose, PT plus 1 transpose is PT transpose times M, or
What is the capital T?
oh, the capital T is transpose. Yeah, so or M transpose times PT is equal to PT plus 1. It depends on whether you want to think of them as row vectors or column. Okay, so that is step 1. The other thing that we know is that our guarantee about M is the following. If someone tells us that I have a spectral gap, I mean, my lambda is a specific quantity. What does that mean? It means that if I take any function that is orthogonal to the all ones function, acting by M shrinks the length of that function by a factor of lambda. So as we mentioned, I want to focus on the vector being whatever was inside here. Pi inverse PT minus 1. Okay. And I'm going to call this as QT minus 1, where QT just refers to this vector. Okay. And I want the following 2 dream scenarios. I'm hoping that the following 2 dream scenarios work. That is, QT minus 1 happens to be orthogonal to all ones. And secondly, if I think of what is QT plus 1 as a function of QT, it really is the evolution of, you think of it as functions and M acts on it as like column vectors. If these 2 were true, then you immediately get the fact that every time I replace T with T plus 1, I'm going to get a shrinkage by a factor of lambda. And now as long as lambda was bounded away from 1, you notice that as T becomes larger and larger and larger, the total variation distance is tending to 0. And in fact, it's going like exponentially down to 0. Okay.
So should be an M or an M transpose in the dream scenario?
No. Because our guarantee about M is just that when M acts on a column vector, then it shrinks. So I can't make the same claim about M transpose. I mean, because that's like saying something about the row vector. Right? But we are somehow trying to say that no, the same thing is true. We have somehow managed to move from
The spectrum remains.
The spectrum remains the same. You just want to say that the eigen decomposition with respect to the columns was something where the top eigenvector was the all ones vector. We somehow want to say that this is dual to some decomposition on the row side, where the top vector is replaced by the stationary distribution part. Okay, and hopefully in your problem set you will work that perspective. Right now we are just sort of trying to bulldoze our way through the calculation and see that works. Okay, so good. So now let's just look at let's try to check if the dream scenarios actually hold. Is the statement 1 and statement 2. Okay, so the first thing I'm going to do is I'm going to look at the vector QT. And let's decompose it into the following form. I want to write it as some A times the all ones vector plus, I don't know, some QT transpose. Where QT transpose is the component that it has on the orthogonal direction. And I just want to get a sense of what is A. And if the dream scenario is right, then A must be 1. I mean, I would like to say that the component that it has along the uniform distribution, all ones, is actually the all ones. So if you subtract that out, you actually get something which is completely orthogonal. Okay, so that is dream scenario. So now how do we calculate A? So same, I mean, like we have gone through this drill multiple times. You just take the inner product of Qt with the all ones vector. That's exactly what A is going to be. Okay, and let's just expand this out. So this is going to be pi of x times Qt of x times 1. Okay, but what is Qt of x? That is nothing but Pt of x divided by pi of x. Okay, and therefore this is just the sum over Pt of x. It's a probability distribution, so therefore this will sum up to 1. So this tells us that A is actually equal to 1. So therefore, dream A is true. Because this is like saying that the vector I cared about, Qt minus 1, is actually equal to Qt per. Okay, it's the component of Qt that is completely orthogonal to the all ones vector. Perfect. Okay, the next thing we want to get a sense of is dream scenario 2 true? Okay, and so let's just again write down what is Qt plus 1. It is pi inverse times Pt plus 1. And how is Pt plus 1 related to Pt? And this is nothing but pi inverse times M transpose applied to Pt. Okay, and this is the point where we are going to use the reversibility, or rather, there was a particular relation that M and pi satisfied, which was, let's just go back. What was the relation? Which was that pi times M equals M transpose times pi. Right? So what do we know? So we know that pi M equals M transpose times pi. So if I multiply both sides of the above equation by pi inverse, what you end up getting is M times pi inverse equals pi inverse times M transpose. I basically took the equation above, multiplied by pi inverse on this side and on this side. So this is what you end up getting. And this basically means that this pi inverse M transpose that I have, this is the same thing as M times pi inverse. And that was what pi inverse Pt is exactly what Qt is. So dream scenario 2 also works. So therefore, the observation that we have, usually when you're dealing with symmetric matrices, this is like a one-line calculation from the definition. But because we are dealing with irregular graphs, we have to do a bit more. But eventually what you do get is the familiar thing you may have seen, which is that if you look at the 2 norm of the difference you care about, okay, as t becomes larger and larger and larger, you keep incurring a factor of lambda. So if you start off with a distribution P0 and you take t steps of your random walk, you will incur a factor of lambda to the t, because every step of the random walk, the vector shrinks by a factor of lambda. Okay, so is this okay so far? It's not a hard calculation, but it's like it feels like completely unnecessary to deal with irregular graphs, etc. But there is merit to doing this, and it's
why did we start with the total variation at the beginning?
So it's just that many times what will end up happening is like you have a certain event that you have in mind. And you sort of want to just say that, okay, this is the distribution I'm supposed to be doing, but I'm instead doing this. And I want to get a sense of how much does my value change. So many times when you're applying it, you'll be using the total variation distance.
I see.
And that's the reason why we are eventually getting to the total variation. Okay, so this is what we have here. But once again, I mean, like, you know, I would like, so we already saw that this was at least as large as the total variation distance of the probability distribution Pt with the distribution pi. Now, eventually, I would like to relate this to the total variation distance of P0 and pi. Okay, so once again, this is like an application of Cauchy-Schwarz. It's sort of easy to sort of notice that this is at most lambda 2 times the, I'll let you figure this out, P inverse P naught minus P all ones, the one norm, and you might have to multiply by a factor of about root n. I mean, this is a standard Cauchy-Schwarz, like to relate the two norm to the one norm. Okay, and a stupid bound here is that, oh, sorry, why did I put a lambda square? I meant lambda to the t. Okay, so this is at most lambda to the t times, it's sort of, you can bound this quantity by just one. Okay, because it's the expected value of some small difference that will turn out. It's easy to see that this is at most one. So a bound that you could have is just that lambda to the t times root n. Okay, so it does tell you that the total variation distance as t becomes larger and larger and larger, it's certainly no more than root n times lambda to the t. So at the face of it, it looks like maybe for the initial few steps, I can't quite say much. But after t is sort of large enough, this total variation distance seems to be shrinking by a factor of lambda all the time.
So this capital N is the number of vertices.
Sorry, capital N is the number of vertices of the graph that we are dealing with. Okay, so many times what we would want to do is the following. I tell myself that I want to get epsilon close to the stationary distribution. And now I just want to get a sense of what should my t be so that I am now guaranteed that I am epsilon close to the stationary distribution. Okay, and if you think about it, what is this going to be? So I'm going to ignore constants. So this is going to look like log of n over epsilon. Okay, divided by log of 1 over lambda. Because it's shrinking by a factor of lambda. And the t that you need to set this up to is going to basically be, I need to somehow make sure that lambda to the t is smaller than epsilon by square root of n. Okay, you just rearrange things. This is what you're going to end up getting. Sometimes people write this as log of n over epsilon by minus log lambda. But whenever I see something like this, it sort of takes me a moment to convince myself that this lambda is less than 1. So this is a quantity that is positive or something. But sometimes it's actually going to be convenient, especially if you want to think of what happens when lambda is this much or lambda is that much, etc. Okay, so far is this clear? I mean, it's not a hard calculation, but it's important that we understand how this proof sort of went. Let me just briefly go over it. So the idea was we wanted to understand what the probability distribution as you take many steps of the Markov chain of the random walk happens. And the distance measure we had in mind was this total variation distance, which is like an L1 distance between these two vectors. But it's L1 with respect to this the uniform distribution. In some sense, you're like adding up all the coordinates. So the first thing we did was some jugaad to make sure that this L1 starts looking like the L1 with respect to the pi distribution we care about. And once we did that, we applied one Jensen and started telling ourselves that we'll deal with the two norm rather than the one norm, because two norms are nicer behaved when it comes to these matrices and inner products and so on. And it just so happened that surprisingly there is justice in this world, and we have the things that we would like to happen seems to happen. And it just so turns out that the definition of spectral norm that we had with respect to M acting on column vectors was sufficient to somehow say that these vectors you care about, as t becomes larger and larger, the lengths do shrink by a factor of lambda. Okay, and then it's a bunch of calculations to basically tell ourselves saying, what is the mixing time if you want your error to be epsilon, and the mixing time is exactly this quantity. But this is an upper one. Like taking t steps where t equals this is sufficient to guarantee that what your current distribution is within epsilon in statistical or total variation distance to the main distribution.
all the norms in those statements are with respect to the pi.
Oh yeah, everything here is all with respect to pi. Yeah. Okay, if we only wanted to argue about the 2 norm instead of this, yeah, we could do that, like in the sense that, but then you will have to somehow justify why you're dealing with this vector. I mean, this sort of normalized, you're taking a probability distribution, but somehow normalizing with pi so that you're looking at a difference of all ones. But in the problem set, I will try and phrase it in such a way that you use the spectral theorem for the rows, and there the top eigenvector happens to be the stationary distribution. And you can just say that anything orthogonal to the stationary distribution according to the new measure you can define, those shrink by a factor of lambda. That will make it perhaps a little easier to get a sense of. All right. So let's look at 2 specific situations of if lambda is this much, what should I expect things to be? Okay, and I'm going to look at 2 scenarios. One where the spectral gap is a constant, that is, lambda is bounded away from 1 by some constant, and I want to get a sense of what should t be. And then we will ask, what if lambda is really close to 1? What should the mixing time be in that case? So the first thing to notice is that, if lambda is bounded away by a constant, bounded away from 1 by a constant, then notice that this log 1 over lambda, this is some constant. Okay, and therefore the number of steps you need when you can guarantee that you're going to have total variation distance at most epsilon is going to be like order log n over epsilon. The constant here involves whatever this lambda is, but if lambda was truly a constant away from 1, then it's going to really go down exponentially. Okay, now let's look at the other scenario where, okay, fine, you do have some spectral gap, but the gap is very small. So the lambda just looks like 1 minus some poly in n. Sorry, inverse poly in n. Okay, now I want to get a sense of what should t be in such a scenario. Okay, so let's again do this calculation. So this is going to be like log n over epsilon by, now I'm going to use this minus log lambda. Okay, and this is going to be,
the bottom is getting chopped off.
Oh, sorry. Is this okay, Akadev?
Yes.
Okay. Oh, here also it's getting, no, here, okay. So log n over epsilon by log of, sorry, minus log of 1 minus 1 over n to the c. Okay. If you recall your Taylor expansion of log 1 minus x, it looks like minus x plus x squared by 2 and so on. So therefore, this is roughly equal to n to the c times log of n over c. Sorry, n over epsilon. Okay. So in this case, it tells us that if you have a spectral gap that is inverse polynomially close to 0, or lambda is inverse polynomially close to 1, then the number of steps you need to take in order to mix well is actually going to be proportional to something like 1 over gamma, if you ignore the extra log factor. Okay. So yes, you can imagine that there are some graphs where if you have a spectral gap, the mixing time is really short. It's like order log n. However, if your lambda is too close to 1, then your mixing time is very bad, in the sense that it's polynomially large in that case. Okay, so
why is in this case polynomial time thing bad for us and log is really the right?
Okay, bad was okay. It's a little subjective. It's just that we would, of course, like it to be as small as possible. And in some sense, if you're dealing with constant degree graphs, notice that log n is the best thing you could hope for. Because if you aren't even taking log n steps, you're not even going to be seeing all the vertices. But it sort of tells you expanders are some of these graphs where somehow it looks like log n doesn't just guarantee that you see all the vertices. You are somehow going to be at every vertex sort of equally light. It's a stronger statement than that. Okay. Now, okay. So in the remaining time, I don't want to start a new topic, etc. So we are going to just use this to analyze the random walk, and then maybe spend some time to get a sense of what happens here. So let's just look at some examples before we analyze the randomized algorithm for ST connectivity. Okay, so let's look at some examples. So just to recall, I'm going to use V1, V2, blah, blah, blah till Vn as the eigenvectors corresponding to the corresponding lambda 1 through lambda n, and lambdas are usually arranged in descending order. Okay, lambda 1 is 1, and V1 is therefore the all ones vector, and then lambda n is the smallest of the eigenvalues. Okay, so first question. So I want to look at situations where the spectral gap is terrible. There is no gap. Okay, because these are situations where things shouldn't mix. Right? Because everything above was dependent on the fact that this lambda was sort of bounded away from 1. Okay, otherwise there's no shrinking that's happening. I mean, it's just going to stay the same. Okay, now when will lambda 1 be equal to 1? Sorry, lambda 2 be equal to 1? What are graphs in which you can imagine that, or you should think of it the other way. The all ones vector is certainly a vector such that if m averages it out, you end up with the same vector. But if someone told you that no, there is a different vector also, which is non-constant, that also has the same property, that if m averages it out, you actually get back the same vector. Yeah, so this means that the graph must actually be disconnected. Because if it's disconnected, you can sort of take the constant value on each connected component. And the averaging operation is obviously restricted to each component, and it will stay the same on each of the components. Okay, is this, and if you formally want to look at this, you basically, okay. So suppose someone gave you an f that apparently is orthogonal to the all ones vector, but still m times f equals 1. Sorry, m times f equals f. Then one way to do this is
but if the component sizes were the same, then you won't get a different lambda 2, right? You have to have different component sizes or something.
No, it doesn't matter. So for instance, if
no, I agree. I agree if G is disconnected, then you need this. But I'm saying, isn't it true then? But you want a multiplicity. You want something other than the all ones vector to be also having the eigenvalue of 1.
Yeah. So all I want is that I want there to be two disconnected. So for example, suppose there were two disconnected components, maybe of completely different sizes. They're not the same size or something. In principle, I can put ones here. And
if they are different sizes, then I agree. But if they are the same size, wouldn't this be still like the all ones vector itself?
No. So for example, if they are actually exactly of the same size, consider the following potential. On all the vertices in one component, I put 1. On all the vertices of the second component, I put -1.
Oh, right. I'm sorry. Yeah.
Okay. So this will ensure that m times f is equal to f itself.
Correct.
And fortunately here, because the components are of the same size, this f happens to be perpendicular to the all ones vector also. But if the components were of different sizes, you will have to ways to look at it. And in fact, in fact, it actually turns out to be the following. It turns out that if you care about how many different lambda i's actually take value 1. So we were talking about when is it the case that lambda 2 is 1. So if lambda 2 is 1, but lambda 3 is not equal to 1, it turns out that the graph has exactly 2 components. Okay. So in some sense, the multiplicity of the eigenvalue 1 sort of counts how many different components do you have. Okay. And in fact, this is lambda 2 is like a robust version of this thing. If lambda 2 is very, very close to 1, you sort of want to say that the graph is like almost disconnected. Okay, what does that mean? Here is an example graph that will have this property. You take two really well connected blobs, but then you put one edge between them. Okay, such graphs are called dumbbell graphs. In the sense, if you take cliques on either side and then you just attach them by one edge, Okay, this is the dumbbell graph. And as you can imagine, if you start your random walk from a vertex on the left-hand side, you're going to end up staying in this left-hand side for a long time, unless you manage to choose this one edge going out. And then you have a chance of mixing there. Okay, so hopefully it gives you a sense. And in fact, there is this, so this is like saying that there is a really small cut that your graph has, but you need to calculate this, measure the cut correctly. And this is usually what is related to Cheeger's inequality. So Cheeger's inequality sort of says that if lambda2 is very close to 1, then in some sense there are like very low conductance cuts in your graph. I'm not defining conductance, so I'm not going into that thing, but there is a way in which you can make this robust. So it sort of tells you that if lambda2 is, or if there are too many lambdas that are very close to 1, it roughly is going to tell you that there are like that many components in your graph and some small number of edges that are connecting them together. Okay. And now let's come to Pavel's question, which is when is lambda n equal to -1? Okay, this is again an example where the lambda of G will then be equal to 1 again. There is no gap. Okay. So this is not suggesting that the graph is disconnected, because connectedness is a question of how many lambdas are equal to 1. Whereas now we're talking about lambda equal to -1. Good. So turns out that when lambda is -1, the graph is actually bipartite. Okay. And what is one way to see this? You want some vector such that MF is equal to -F. That's what it means to say lambda is equal to -1. Now let's do one thing. Let's focus on the coordinate in F that has the largest positive value. Okay, there is some largest positive value or largest negative value. Without loss of generality, let's assume that it's more positive than negative. Okay, let's look at the largest positive value. Now, what is MF going to do? It's going to average this over its neighbors. But all its neighbors have absolute value at most whatever I started off with. And furthermore, if I'm supposed to get minus of the value I started off with, all my neighbors must actually have negative values and equal to what I have. That's the only way a convex combination will actually give me -F. So if you think about it, if you just look at F, take all the positive guys as one set and all the negative guys as another set, you can see that all edges in your graph must actually go between these two sets. Okay, so that's the way of building a bipartition by looking at this eigenvector. Or conversely, if you know that your graph is bipartite, you just put positive values on one side and negative values on one side. Just set it up in such a way that the averaging actually, the values are arranged in such a way that MF is equal to -F.
Of course, doesn't say that this is an if and only. Like
yeah, so this is also an if and only.
It is?
Yeah. Oh, sorry.
You have a bipartite expander. How can this be -1?
Sorry, what?
So you're saying in a bipartite expander?
It doesn't matter if it's a bipartite expander. Even if it's a bipartite expander, lambda n, the way I have defined it, will be -1. So I want to say that this is equal to this if and only if G is bipartite. Okay.
No, but if it is not complete, because
am I missing something here?
No, it makes sense. Like if you have to bipartite graph, then you cannot converge to.
Yeah, you can't converge to states. No, I guess Arkadesh's point is maybe there are non-bipartite graphs which will also have -1, but I don't see it because I basically want to say that if I take S to be the set of all I, such that f of I is greater than 0, and E to be equal to S complement.
Ramprasad?
Yeah.
I didn't say that. I was saying that I don't necessarily see why, if it is a bipartite graph, I mean, the way you argued, it implies that if the lambda n is -1, if you have a -1 eigenvalue, it has to be bipartite. That's clear.
Yeah.
See, sorry, my stupidity, that if it is a bipartite, then it implies that lambda n would be -1.
Yeah, because you can set up, like if your graph looks like this,
yeah,
and you can set up a certain function here,
So let's maybe take an example. Take a regular bipartite graph.
So for example, if you take a regular, like if you take a biregular bipartite graph, just for simplicity,
Yeah.
okay, that is both sides have the same degree, etc. Just the vector that assigns 1 here and -1 here is actually an eigenvector with eigenvalue -1.
Oh, that's true.
Yeah, so it tells you that for a bipartite graph, I can indeed see lambda n equals -1.
I see. Okay.
Right? In fact, there's a stronger statement that is also true, which is how many different lambda i's can be -1?
I see this. I see this. Okay. Sorry. Yeah.
Okay. How the, like, for example, if the last, I don't know, last 4 guys turn out to be -1, what does that mean? Well, it actually turns out that it is actually 5-partite in that case. So that is, there's a bunch of subsets and all edges only go across things. There are no edges within blobs. Okay. Now this is of course a bipartite graph because I can think of this as one partition and this as the other partition. But like having multiplicity at -1 sort of refers to the k-partiteness. Like how partite is your graph?
Yeah. So I have two questions. When we were doing this if and only if for it being bipartite, I mean, it felt like we were using that some eigenvalue is minus. I mean, were we using the fact that it's the
Yeah. So I was using some value is -1. So, and because it has to be orthogonal to the all ones vector, I assume that something must be positive and something must be negative. Because it must sum up to 1.
Yeah, but I mean, it needs, I mean, that n, the fact that it was the last eigenvalue, the smallest.
But if lambda something is 1, then lambda -n will also have, because they're all bounded between -1 and 1. So, okay. So, and here also you can sort of see that the random walk cannot mix, right? Because if you put all your distribution on one side, your random walk is always going to oscillate between the two sides. Okay, we cannot say that it's 5-partite because there are some edges between the 4 parts below. No, I think it's 5-partite just means that there is a partition of the vertices into 5 parts such that all edges are across the parts.
There are no edges within the.
There are just no edges within each part. So in a bipartite graph also you have S and T, and no, it is bipartite because, like, okay, let me maybe draw it the following way. So here is an example of a 3-partite graph where all edges only go like this or like this. Oh, sorry. Am I mixing up something?
No, it is not bipartite.
It's not bipartite. Sorry. Then I'm maybe messing up. Yeah, there's some definition of k-partiteness that shows up here, but now I'm getting confused. Oh, thanks a lot. So it's not the same thing as k-partite. Yeah, because you could have triangles now. Yeah. Because k-partite, bipartite graphs aren't supposed to have triangles. Good. Thanks a lot. I mean, okay, what I'm saying is not true. There's something about k-partiteness that shows up, which I'm now forgetting. Okay. Anyway, let's. If I remember it, I'll add it on this thing. Okay. So one of the problems that will be there in your next problem set is going to be the following, which is that if you actually have an undirected graph that is deregular and it's connected and it is not bipartite. These are two bad situations when either lambda2 or lambda n actually end up at 1 or -1, right, respectively. So if you assume that these two don't happen, that is, it's a connected graph and it's a non-bipartite graph, you can show that there is always going to be some spectral gap. In the sense that the spectral gap is bounded by something like 1 over dn squared. Okay, like it can't be like really close to 1. It's away by some polynomial factor depending on the degree and the number of variables.
So this statement, is this the starting point for rainbow?
Yeah,
This gap.
good. Exactly. This is the starting point. In fact, the starting point of rainbow is the algorithm that we mentioned. So this basically, if you go back to what we had seen earlier, which is that if your lambda looks like 1 over n to the 1 minus 1 over n to the c, we said that the mixing time is something like n to the c. I mean, if you ignore logs. Okay, and now this is going to therefore say that if I run for something like dn squared steps, again ignoring logs, then that is enough for the random walk to just mix very. Okay, so let's use this to analyze this. Yeah.
One question to lambda. Is it also known Is there like a robust version of?
Yeah,
like
there is.
there's a-
There is. I
It's
don't know if
probably-
people here took the toolkit course of Prahlad. It seems like I'm going to borrow a lot of assignment questions from his assignment. So there is a close to bipartiteness also, which lambda n being too close sort of also captures. Okay.
Sorry, so is that problem set thing?
Uh-huh.
So let's say we are only looking at deregular undirected graph.
Uh-huh.
So we know that anyway we know that lambda. So for bipartite we know that it's bipartite you can only have lambda n is
-1. Yeah.
And what this is. So they're saying you can always expect at least some gap. Like if lambda n turns out to be like for some small constant 1 minus epsilon.
Lambda n is like -1 plus epsilon.
-1 plus epsilon.
Uh-huh. So this is sort of saying that if the graph is not bipartite, that is enough for you to say that lambda n is like away from -1 by at least this much. Like you can't be sort of exponentially close to -n or something like this. You need some lower bound to sort of say that if you are not -1, I want to say you have to be away from -1 by at least some quantity. That at least some quantity is something depending on both d and n. And that's what you have here. Like most of the time, we don't really care about this exact polynomial. All I want is some polynomial bound, like inverse polynomial lower bound, because that will allow me to say that, if I run for this many steps, then this random walk mixes well. So let's look at this algorithm for graph connectivity that we spoke about last time. Okay, we just briefly mentioned this. Can I have the intuition that we can only have dn edges, therefore dn squared follows somehow? It's sort of similar the way
Why this algorithm works?
no. Why is the value dn squared? There are dn edges, so maybe it's reasonable to expect 1 over dn, but there is an n squared that shows up. I don't know of a very simple way of saying why that is the case. In the way the proof sort of works is you just decompose your graph as paths and somehow argue based on that. Yeah, I don't have a very quick way to sort of see why this is in some sense, the right answer. But yeah, okay. Now let's look at this algorithm for graph connectivity. And I'm going to make life simple and deal with the following situation where you have a deregular undirected graph, and let's say you promise that it's not bipartite, just so that I want to apply the above statement. Okay, and you're given two vertices S and T. Again, I want to know is S and T connected in this graph or not. And what was this low space algorithm that we came up with? We basically said, let's start with this vertex S, and I'm just going to keep taking a random walk for some R steps. Okay, and at any point, I'm going to basically ask, okay, I'm at some vertex, is that vertex T? If it is T, well, of course, I found T, I accept. But if I haven't seen T after taking R steps of this walk, I somehow want to say that, I should be able to say that, this is not, my graph is not, S and T are not connected. And I want to analyze how well does this graph perform? Now, obviously, if S and T were not connected, starting a random walk in S is never going to see T. So what we want to argue is instead the other way. That is, that's why if we are dealing with a connected graph, in which case I know that because it's non-bipartite, there is some spectral gap. Okay. So if we are dealing with a connected graph, I want to say, what is the chance that you do notice T when you start a random walk at S? And I want to say that that number is sizable. There should be a decent chance that you encounter T. Okay. So let's analyze this. So I'm going to start with the probability distribution P naught to basically be, there is 1 at the Sth coordinate and 0 everywhere else. That's the same thing as currently my V is equal to I'm starting my random walk at the point S. All right. And then this distribution evolves. Okay. So I keep going at the end of it. Maybe I'm at some PR. transpose, which is some distribution. So that again is going to be V is equal to some vertex. Let me call this V0, I'll call this V1, and in general VR. Where each VI is like a sample of the, I mean, it's sort of, if you think of the marginal distribution on VI, it's distributed according to the PI. Okay. And let's in fact simplify everything and just ask, what is the chance that VR is equal to T? I just want to know, I do R steps of the random walk. I just want to get a sense of what's the chance that this is equal to T. Okay, technically speaking, the algorithm is checking everything in the middle, but let's just focus on that to get a sense of things. Okay, and I'm going to, let's keep track of this pi. Now notice that because I have assumed that it is D-regular, the state distribution is just going to be the uniform distribution on all the vertices. Okay, so that is just going to be 1 over n, blah, 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 till 1 over n. Okay. Now I know that as R becomes larger and larger, this distribution.
The bottom is getting chopped off. Sorry.
Oh, sorry. Yeah. As R becomes larger and larger, the distribution PR is sort of getting closer and closer to pi. Okay. Let me put a transpose because I've written it as a row. Okay. What do we know right now? Suppose I tell myself that I'm going to run it for enough steps so that this total variation distance becomes, I don't know, smaller than something like 1 over 100n. Okay, that's what I'm going to do until I can guarantee this. My R is going to set up such that that happens. Then I want to claim that the probability that VR is equal to T better be at least 1 over 2n. Because the Tth coordinate here is 1 over n. If your total variation distance itself is like 1 over like 100n or something, you better be within 1 over 100n of 1 over 2n. Okay, I'm just being a loose bound and saying that it's at least like 1 over 2n. That's it. So you have to be within 1 over 100n of 1 over n, and therefore you'll have to be at least 1 over 2n. Okay, so if I ignore all vertices I have seen so far and just open my eyes at the Rth step, the chance that I am at T is even there is sizable. There's at least a 1 over 2n chance that I am at T. Okay, so if we just repeat this algorithm something like 2n squared times, that is, I close my eyes for R steps, open my eyes at the Rth step, and then see, am I at T? Okay, if I found, then I accept. Otherwise, okay, fine, let's throw this away. Let's start the random walk again, and then open my eyes at the Rth step, and am I at T? So if you do this like 2n squared times, the chance that you end up missing T every single time, okay, this is at most 1 minus 1 over 2n, the whole power 2n squared. Because 1 minus 1 over 2n is a chance of you missing it in one run. But if I run it so many times, this is what will happen. And this roughly looks like e to the minus n. Right? Like 1 minus 1 over n, the whole power n is like 1 over e. And there is an extra factor of n I added just so that this becomes exponentially small. So which means that with exponentially small probability, one of these, if you run this algorithm, whatever, 2n squared times, you will definitely encounter the vertex T in one of those runs. Okay. And this is very similar to just saying, I'm going to run a random walk for 2n squared R steps. Rather than saying that I will run it for R steps, abort and start again, abort, start again. You can do the same analysis. Yeah, it doesn't matter anyway. So so you can just imagine that at this point I'm at some vertex. It's not equal to T, but doesn't matter. Let's imagine starting the random walk from here onwards. And that will basically allow you to say that as long as you run it for 2n squared R steps, you will encounter T with high probability. And we just notice that R never has to be more than poly in n and D. Like R only has to be something like dn squared or something. So you run it for something like dn to the 4 log n steps, and then you're perfectly fine. Okay, is this okay so far?
And where is it showing up that the spectral gap is 1 by poly?
So because I need to get a sense of what should this R be. The R I'm doing so as to ensure that the total variation distance was at most this much.
You need it. Okay. Yeah.
So for that, I need to set R appropriately. And that definition of, I mean, like the calculation for R ended up involving whatever the spectral gap was. Where was that? Here. Yeah. Okay. So in the remaining 10 minutes or so, I'm just going to tell you about what is going to happen next, which is there's a beautiful result of Rheingold, which we will see after we learn to build expanders, etc. Which is we just saw a randomized algorithm for ST connectivity above. Okay, that uses only logspace. That is, you're only remembering a few counters and what your current vertex is or something like that. Okay. Rheingold actually showed that no, in fact, you can actually get a deterministic algorithm that actually uses just ordered log space. Okay, so I'm going to give you just a rough roadmap of how Rheingold's algorithm works, and to give a sense of how this de-randomization happens. It's a very beautiful idea. So the key idea was that the following dream scenario. So you start off by assuming that let's assume that your graph is deregular. Firstly. Okay, that is usually easy. Like you can take every cloud and replace it by a cycle there or something. There are some standard tricks you can do to convert connectivity in a way that things becomes deregular. Okay, and let's assume that D is a constant. Okay, and let's even make an even bigger assumption, which is that, okay, there is some component that contains S. I'm going to assume that that component is actually a very good expander. Okay. Now, in that case, do I have a deterministic log space algorithm? And the deterministic log space algorithm is just the following. I know for a fact that if I take paths of length order log n, that is, if I take a random walk of length log n, it completely mixes in the component that contains S. So what we will do is we will just explore all possible paths of length log n. This takes a little bit of thought to sort of see that, exploring all parts of length log n in a constant degree graph, you can actually do it in log space. If you systematically label the vertices going out, like the edges going out of a vertex, you basically always tell yourself that I'm going to explore edge 1, edge 1, edge 1. But if my counter has gone back, I return, and then if I say, oh, I went via edge 1, now I go via edge 2. So there is a standard way in which you can explore all parts of length log n using just log space. Okay, unfortunately, because the graph is only deregular and D is a constant, D to the log n is only polynomially large. So the mixing of expanders will tell you that if T is in the same component as S, I better see T within this much time. Okay. So this is the analysis. This is what you do if your promise that your graph is deregular and your graph happens to be an expander in each component. Okay. And the key technical part of Rheingold's analysis is to somehow get to this dream scenario. You start with an arbitrary graph, and then you build a graph that is an expander in each component in somehow using only log space. Now, this is like a very non-trivial thing to do, is because you won't actually be able to write down this graph at all, because you don't have space to write this graph down. This graph is somehow going to be implicit in the...
So you don't want to affect connectivity.
You don't want to affect connectivity. You want to do it in a way such that the connectivity is preserved, but you somehow managed to make every component an expander. But you're never going to write down these new edges that make your components an expander, because you won't be able to write them down because you can't use that much space. So there's something very implicit that will go on here, where you're essentially going to make every connected component of your graph into an expander. That's where the key technical part of Rheingold's theorem goes into. Okay, so we will see this maybe in 2 classes from now. Next class will likely start building expanders, and then after we are comfortable with that, we'll then be able to. So basically, the next class I'm going to follow with something called the hitting property of expanders, and we will see how you can use this for randomized algorithms when you want to reduce the error but not use too much randomness. So this will amount to saying that you have a certain bad set, And if you take a random walk starting at a random vertex, what is the chance that your walk is completely contained in this back set? So we want to say that you will end up hitting every large set or something. So we'll look at this hitting property. And before we build expanders, etc., in fact, even to prove the hitting property, there is this beautiful decomposition that we will do, which will morally, like sort of, it's a formalization of what is sometimes like used in intuition, which is that you want to say if something is a good expander, good spectral expander, we will say that its random walk matrix looks like a convex combination of the random walk matrix of a complete graph, which is like the best expander you could hope for, plus some error term. Okay. And this perspective will be very useful because many times when you're dealing with expanders, you sort of say, you sort of think this should hold. Why do you say you believe this should hold? It's because that holds in a complete graph. And this will sort of let you say that, okay, you are gamma correct. There is a 1 minus gamma of this error that is sticking around, and hopefully those are error terms that you will take into account. So in the next class, we'll do this sort of matrix decomposition. It's not very hard, but it's a really powerful like sort of starting point to have for all calculations involving expanders. And once we do this, we prove the hitting property and then slowly start building expanders. That's going to be the agenda for the next couple of lectures. All right. So, are there any further questions? If not, we'll stop and we'll